Hey, how are you doing, guys? I'm Rohan. Here's lesson 11, so let's get started. In this video, we will cover TabNet Model, then we are going through the time series, so let's get started with our lesson. Let's begin with TabNet. So TabNet stands for Tabular Attention Network, and it's designed to handle structured data or tabular data, which often includes data organized in rows and columns. TabNet incorporates elements of both deep learning and attention mechanisms to make predictions on tabular data efficiently. For today, we will be utilizing Michael Grankin's Fast TabNet wrapper. Here we install Fast TabNet. First, let's build our data real quick. So we're going to use adults dataset again. Here we import tabular module from FastAI. Then we grab our dataset by calling UntiTheData method. And here we create our data frame by calling pandas.readCSV. And now let's build our tabular pandas object and the data loaders. First, we start by defining our categorical and continuous variables, the preprocessors that we are going to use like category 5, fill missing, and normalize. And we are going to use random splitter to split our data. And here we build our tabular pandas object by passing it our data frame, the preprocessors, our categorical and continuous variables, our dependent variable, and the splits. And then we create our data loaders and we define the batch size to be 1. Now let's take a look at how the patches feed into our model. As you can see here, here's our categorical, so they are encoded. Then we have our continuous variables, and as you can see, they are normalized. And the last tensor here is corresponding to our y, which is the output. And here we built our tabular learner as we used to do. And now we can show some basic visualization of this model by using fast.library. So here we import it. Here's a basic rundown of our model. So as you can see here, we have our pre-processed input that fed into an embedding matrix and drop out for categorical inputs, and batch normalization for our continuous inputs. Then we go through 3 fully connected linear batch norm drop layers. So this is for our FastAI model looks like. So it's not very big. We have only 3 fully connected layers along with an embedding matrix. Now let's see how does it compare with TabNet. So TabNet is a very deep model. This part here is what a TabNet model looks like. We still pre-process the input, so pass it for embedding matrix, then drop out for categorical, and batch norm for continuous. And then we concatenate those values and feed them through what is essentially TabNet is. So it has 2 transformers followed by a final mapping, which are attention transformer and feature transformer. And then we get 4 outputs. That's because TabNet operates by putting a mask over each value as it's passed in. And with that mask, we can see and adjust how each of these values were affected more or less. So that's why we have these masks, mask explain, mask loss, and the actual output. And for today, we just care about the actual output. Now let's take a look at these 2 transformers. For feature transformer, we have these 2 linear layers followed by what is called a glue block. So glue block enhances the model's ability to capture complex feature interactions and help us in modeling dependencies in tabular data. You can read about it if you want. And for the attention transformers, we start with the linear layer. Then we go through a ghost batch norm. And then we do torch multiplication of our current input and the prior. And lastly, we do sparse max activation on it. And for that, we can call the attention transformer the encoder and the feature transformer the decoder. And now let's take a look at how we fit that into the framework. First, we need to grab the embedding sizes. Here we call get embedding sizes and pass it our tabular pandas object. And here's the results. Now for the TabNet model itself, there is a lot of hyperparameters that we can mess with. So we have ND, which is the dimensions of the prediction layer, usually between 4 and 64. NA is the dimensions of the attention layer. N steps, the number of successive steps in our network, usually between 3 and 10. Gamma, which is a scaling factor for updating attention, usually between 1 and 2. Momentum, N independent, which is the number of independent glue layers in each block, and the default number is 2. N shared, the number of shared glue layers in each block, and also the default number is 2. Epsilon, which should be kept very low to avoid log 0. Now let's build one similar to the model that we showed above. To do so, we will set the dimensions of the prediction layer to 8 and the dimensions for the attention layer to 32 and our steps to 4. The first thing that I want to show here is how we incorporate TabNet using fastai code. So all of this here is fastai code, and also all of this here is fastai code. And now let's go through this code. For the init method here, it initializes TabNet model class. It takes several hyperparameters as an input, including embedding sizes, the number of continuous features, the output size, embedding dropout rate, and more. It first creates embeddings for categorical features using NN module list and embedding layers. Then it defines a dropout for our embeddings and batch normalization for our continuous features. Then it calculates the total number of embeddings and stores them as class attributes. And lastly, it initializes TabNet no embeddings model, which is a component of this TabNet model with various hyperparameters. For the foreign method here, it takes the categorical and continuous data along with an optional attention flag. So if there are a categorical embeddings, it applies the embeddings, dropout, and concatenates them into a single tensor. If there are continuous features, it applies batch normalization and concatenates them with the previous tensor. Then passes the concatenated tensor to our TabNet no embeddings model, producing our predictions, the mask class, mask explain, and masks. And if y range is specified, it scales the predictions using the sigmoid function and the given range. And if attention is true, it returns our predictions, the mask class, mask explain, and masks. Otherwise, it will return the predictions. And as I told you, we just care about the prediction. So first, we need to make a new data loaders because we currently have a batch size of 1. So here we call a data loaders and we specify the batch size to be 1024. Then we build the model, so we pass it our embedding sizes, the length of our continuous names, the number of classes we have. In our case, we have 2, as you remember from the previous video. Then we pass it the number of NDNA and the number of steps. And finally, we build our learner with our data loaders, our model, the loss function, which is the cross entropy loss flag, the accuracy metric, and we are going to use ranger as our optimizer. Now we can call fit flat cosine for about 5 epochs, and you can see we get around 83.6%, and it doesn't take very long to train. And this code here is for you to play with. And now let's go with the time series notebook. So the module that we are going to work with is Time Series AI 2 by Ignacio. And the essential goal here is we can use arrays of any dimension instead of just one, such as tabular, or three, such as images. So first we need to install the GitHub version. Then we import all the libraries that we are going to work with. For the data, we'll be utilizing the UCI repository, which has 128 univariate and 30 multivariate datasets. In the framework, we can quickly grab any dataset we want. So here is the name for the dataset that we choose, which is starlight curves. Now we can get our data by calling getUCRData and pass it the name of the dataset that we want, along with some parameters to adjust like verbose and onDisk. And it will return the X train, Y train, X valid, and Y valid. And as you can see, we have a very small training set, about 1000 examples. And the validation set is larger than our training data. It's about 8,000 examples, so it's a very interesting problem. And since the data is already split between train and test in the UCR dataset, we are going to merge them and create some indices to split them in the same sets. Here we define the x variable to represent our inputs by calling np.concatenate and pass it x train and x valid. And also we define our y's by concatenating our y train and y valid. Then we call np.save to save the x and y on the disk. And now we can load them, and this mmap parameter here specifies that the file should be memory mapped in read-only mode. So memory mapping allows you to access the data in the file without loading it entirely into memory, which can be very useful for large datasets. And here's our splits. For the first element here, we generate an array of integers starting from 0 to the length of x train. And then we generate another array starting from x train to the length of x. And since we use neat maps, the data is being directly read from memory. Now to make and use your own data, they need to be in three-dimensional array with a format of number of samples, number of variables, and the length. To use this, we have a special TS tensor built to handle this problem. Here we call it and pass it the x. And as you can see, the number of samples is 9,236. The number of variables is 1. And each time length is 1024 samples. Now we can directly use this in our data block API. We just need to define our splitter and getter. So we are going to use index splitter. For getter, we are going to use item getter. 0 for our x's and 1 for our y's. Now we can call data block and define the blocks to be TS tensor block for the inputs and category block for the output. Then we pass it our getters in the splitter. Next, we need to zip up our x's and our y's. For that, we're gonna use itemify, so it will do it for us. Here we call it and pass it our x and y. And now we can make our data loaders. And if we show a bunch of our data, so it looks like a bunch of graphs. And now we want to ensure that the data is still on the disk, so we can look at the data loader.dataset. And as you can see, the meat map. Now let's train our model. So the particular model that we are going to use is called Inception Time Model, and here's its link. So you can go with it if you need more information about it. So all we need to do is to pass it the number of input classes and the number of variables. As you can see, the number of the expected classes is 3. Then we grab the number of variables, which is 1. And now we can go ahead and make our inception time model by passing it the number of variables and the number of classes. And here we can make the learner by passing it the data loaders, our inception time model, the loss function, which is cross entropy loss flat, the accuracy metric, and we are going to use ranger as our optimizer. Now we can find the learning rate and fit, so we are going to use the suggested learning rate, which is about 0.025. And then we fit for 10 epochs, and here's the results. And that's it for today's video. Hope you enjoyed.